Now coming to the second part of the compilers. So here we'll be learning about the lexical analyzer. Lexical analyzer is nothing but the first phase of the compiler, which is also called as the linear analysis or the scanning. So in this, it produces the lexical analysis. It is going to produce the tokens. So whatever the series of characters or the statements are going to be scanned sequentially, and these stream of characters are going to be divided into tokens, which makes up the program and which is going to be read from left to right, and they are going to be grouped into tokens that are nothing but the sequences of characters which are going to have a collective meaning. Now, this lexical analysis is going to be performed using two methods. One, we call it as recognizing the basic elements. The other one, we specify it as recognize syntactic units, and then how do you. So in this, the basic elements are going to be placed into tables, and it is going to specify or store the information such as the precision, length, type, as well as the storage classes are going to be stored into the symbol table. Now coming to the diagram below, if we observe in the diagram, we have a source program which is being written in high level language, and this is being inputted to the lexical analyzer. So this lexical analyzer, in turn, it is going to convert the characters or elements into the tokens, and it is being sent to the parser. So this parser is going to accept the token, and then it processes it, and it sends a request to the lexical analyzer to requesting for the next token, and this process is being continued until unless it completes all the elements. That is, it is going to construct a parser tree. Hence, the lexical analyzer as well as the source lexical analyzer as well as the parser are going to depend upon the table which we call it as a symbol table. Now, what is this symbol table and what exactly it is going to consist of? So this symbol table contains all the identifiers along with their types, length, precision, as well as the storage class, which are going to be stored so that the symbol table makes it easier for the lexical analysis as well as the parser to perform their operation. So upon receiving the next token command from parser, the lexical analyzer reads the input character until it can identify the next token, as you have already seen in the previous diagram. So the compiler is going to have the basic elements or the tokens which are going to be delimited by blanks, operators, and special symbols. So one such task is nothing but stripping out from the source program, that is the commands and the white spaces in the form of blank, tag, and the new line characters. So this also performs another task as user interface. So here this is going to identify, the lexical analysis phase is going to identify the identifiers, then literals as well as the terminal symbols. The main purpose of this lexical analysis phase is it removes the white spaces as well as the commands from the source program. And lastly, it is correlating another error messages from the compiler with the source program. So coming to the syntactic limits, how exactly the syntactic analyzer is going to perform the operation here. So this is nothing but the second phase of the compiler, wherein once the program is being broken into tokens during the lexical analysis phase, so this is being sent to the parsing or the syntactic analyzer. So what happens here, it takes these tokens which is being produced by the lexical analysis as input and generates a parsed tree, which is nothing but what we have already learned in the first part of the compiler. So here it is going to recognize the phrases such as the tokens as well as the identifier, statements, terms, etc. And then it is going to interpret the meaning of those constructions. Now as we are associated with this, each syntactic construction which is being defined, and then we are going to verify the meaning. This is being explained here below, as you have already learned that we have statement. S stands for statements, which is going to derive an identifier. So in this case, as it is going to generate the parse tree, so we are going to have the identifier which is being specified or initiated as an expression. So this derives an expression. So the expression, as you see in the diagram, that is nothing but the parse tree. So statement is going to derive an identifier which is equal to an expression, and this expression again derives an expression plus the terms, and then a term, and then the term is going to derive the term into the factor, and then this term is going to derive the factor in turn derives the expression or an identifier. So here if you observe that we have the parse tree which is being generated during the syntactic phase. Now coming to the semantic phase, once the syntax of the statement has been ascertained, then we move on to the second step to perform or interpret the meaning of the statement, which is nothing but the semantics. So this semantics form, it is going to check whether the parse tree follows the rules of the language. That is, it has to check all the rules which are being defined by the language which we are going to use it. And also it keeps track of the identifiers, their data types, and the expressions. So in this, they use the rules, that is nothing but the reductions, which are going to specify the syntax form of that particular source language. And then these reductions define the basic syntax constructions and the appropriate compiler routine that has to be executed for the constructions, and then it has to generate either the code or an intermediate form for that particular construction. So for example, we have sum is equal to a plus b, and then we are going to define the data types for the three variables, that is int a, sum, double, and then character for b. Now if you observe in this, syntactically it generates a parse tree which is matching, and it doesn't have any problem in generating the parse tree wherein it identifies the different of the three identifiers. Whereas with respect to the semantic form, that is, it has to check for the rules whether it satisfies all the rules which are being defined in the program. So if you observe here, we have sum is equal to a plus b. So we have defined the data type as double, and then A is an integer format, whereas B is a character format. So if you observe here, int and character will not match. So during the semantic form, it breaks the rules and there is a mismatch between the two data types, as we cannot add a character type along with an integer type. So the semantic form is going to check for the exact match, and then it verifies semantically the expressions which are being. Now coming to the fourth form or the fourth phase of a compiler, it's nothing but an intermediate phase. Now till now you have learned about the lexical analysis phase, syntax phase, as well as the semantics phase. Now we deal with respect to the intermediate form. So this intermediate form is going to convert the source program into the machine language or the machine code. So this program lies between the high level language as well as the machine language. So if you observe here, it is nothing but an assembly language which is going to lie between your high level language as well as the machine level language. Now let us take the example, the previous example. So if you observe there in the syntax phase, we have the parser or the tree, that is nothing but the parse tree, which is going to be generated by the syntax analysis, and then it is being sent to the checker, that is nothing but your semantic analyzer, wherein it is going to verify semantically which is being the code which is being generated by the syntax analyzer, and then next it is being sent to the intermediate code generator. So this intermediate code generator is going to give the code which is already converted into the intermediate code. That's nothing but for example, in the previous examples you have observed there, we have three address code which is commonly used with respect to an intermediate code. That is, we are going to reduce the expression in terms of the intermediate code, and then this will be sent to the code generator, which is going to produce the output or the object code in the readable format, and then that is being identified as your target code. Now what are the two advantages? So there are two advantages. Mainly, it facilitates the optimization of the object code. The other one is it allows a logical separation between the machine independent, that is nothing but we have the phases like lexical analysis, syntax, as well as the interpretation phase, and the other one is nothing but your machine dependent phase, wherein we have the code generation as well as the assembly. So using this, it is going to generate the code that is readily available in the executable form for the machine. Now here we have two questions. How exactly this intermediate form is going to perform the operation? One, in what way or in what form? The other one is, what are the rules for converting the source code into the object code or the target code? So this form depends on the syntactic construction, such as the arithmetic, non-arithmetic, as well as the non-executable statements. So in this, now coming to the three syntactic construction, as I've already told in the previous slide, that we have three constructions. One is arithmetic, non-arithmetic, as well as non-executable statement. Now what is the arithmetic statements? So one form of the intermediate analyzer is nothing but an arithmetic statement which is going to produce a parse tree. So this parse tree specifies certain rules in order to create or generate a parse tree, that as I have already discussed in the earlier topics regarding the parse tree, wherein we have the statements, then the identifiers, the terminals, as well as the factor. So here also we specify the terminal node of the tree as a variable, and then every operator, for example the addition, subtraction, multiplication and so on. And then we construct a binary tree wherein the left hand branch is the tree for the operand 1 and the right hand branch is the tree for the operand 2. So we have already discussed this with the examples in the first part of the compiler. Now in this case, the operands are nothing but the uniform symbols which are going to denote either a variable, it can be a literal or any other matrix entries. So the matrix that would be generated for the arithmetic statement is already been explained in the previous topics. So here the tree represents the assignment statement, like the example we had in the previous one, x is equal to a plus b into c. So the operators will be equal to, plus, as well as into, and then we have the variables, or we call it as an identifier, such as a, b, c, as well as the sum. So the reader can form the tree of a particular statement using the rules of the elementary algebra. So the process of constructing a tree or a matrix for any arithmetic statement is subject to the compiler which we are going to use. Now coming to the non-arithmetic statement, second one. So in non-arithmetic statements, it is similar to the arithmetic one, but here the statements we are going to use are do, if, go to, like as we use in Fortran and other languages, etc., can be replaced by a sequential ordering of any individual matrix entries. And then the third one is nothing but your non-executable statement. So these non-executable statements, such as the declare or Fortran dimensions, they give the compiler the information about, or it clarifies the referencing or the allocation of the variables as well as the associated storage. That is, you're going to store the data. So there is no intermediate form for these statements. Instead, the information is going to be, that is for the non-executable statement, is going to be entered into the table which is going to be used by the other parts of the compiler. For example, we have a declare statement, and then this, it is being interpreted during the intermediate phase, such as we identify the data types, the precision, length, and then the storage class which is being specified as the identifier table. Now in many of the high level languages, like any programming languages, some storage allocation and data definition are delayed until execution time, whereas certain tables are used by the object program as well as the compiler. So this is dealt with respect to the intermediate form.